So let's look at the impulse train. Now we have an intuitive understanding of an impulse train. We're going to have the time axis here, and we're going to have an infinite number of little spikes, and they're going to be separated by a particular period. Now the period here is given by large t. So from this spike to that spike, the period is t. From this one over to there, the period, that's going to be a distance of 2t, and so on and so forth up to nt. And the opposite direction here will be minus t, minus 2t, minus nt. So if we were going to represent this impulse train as a little function, we could start off with the impulse. Now the impulse is given by delta t, and we'll have a look at the impulse function just in a second. So we'll have this one here, which is delta t. Now the next one is going to be delta t delayed by a factor of t. So in order to delay the function by t, you simply take the delta t minus t. And if it's delayed by next function here, next spike will be delta t minus 2t, and then minus 3t, and up and so forth. And in general it'll be delta t minus nt. Of course, if you were coming the opposite direction here, it would be delta t plus nt. So if we wanted to represent this impulse train as a function, we would simply have to add up all of the individual impulses. So we'd have to add up all of these. So this is the function we end up with here. So it's going to be the sum from n equals minus infinity to plus infinity of delta t minus nt, and this is going to be our impulse train, which we'll call delta t of t. Now I've got that small subscript t there, it's just telling us that it's a time-based impulse train. So let's have a look at the delta function. This is sometimes known as the Dirac delta function. So the idea about this is that we have a spike that's infinitely high and infinitely narrow, and the area underneath the spike is given by 1. So obviously we don't represent the spike by an infinitely high value, we just represent it as the area. So we say the height of this is 1, but the 1 here actually represents the area under the spike. So this isn't a function as such, it's actually what would be called a distribution, but for all intents and purposes, for what we're interested in here, we'll just call it a function. So we can write this function down. We can say delta t, well, it's going to equal a value of infinity whenever t is equal to 0, and it's going to equal the value of 0 for all t not equaling 0. And the main point here as well is that the integral from minus infinity to infinity of our function delta t by dt equals 1. So that's telling us the area under this little function is a value of 1, and we can see how we're going to produce this function. If we had a little rectangular function and the height was the length here was epsilon, then in order to make the area 1, the height there would have to be 1 upon epsilon, because epsilon cancels with epsilon, you get a value of 1. So if we were to look at halving this length epsilon, we'd have to double the height, and if we kept halving and doubling, then this thing here would tend towards a spike which is infinitely narrow, infinitely high, and it's got an area of 1. So we notice all we're doing here is we're using an even function in order to produce this. Okay, so we could use any even function. Here's another even function here. So we could look at a triangular wave, a triangular pulse, and if we were to halve the distance, we would have to increase the height to keep the area as 1, and so on and so forth. And this thing here will tend towards a spike as well, and we could use a sinc function to do the same. So really what we're doing is, in order to produce this delta function, we're taking the limit as epsilon tends towards 0 of any even function, and it'll tend towards this delta function. So we're interested in finding out the Fourier transform of our impulse train. Now before we find the Fourier transform of the full impulse train, let's look at just the Fourier transform of a simple impulse. So in order to get the Fourier transform, we'll look at it analytically and also in a little geometric sense. So analytically, it's going to be the integral from minus infinity to infinity of our function, which is delta t e to the minus I omega t by dt. So this is the equation for our Fourier transform. It takes the time domain function and it transfers it to a frequency domain. So this is rewritten here. Now the thing to note here is that we know that delta t only exists an infinitesimally small region next to the origin. And we also know that this function here, delta t, is an even function as well. So we can say that the integral from minus infinity to infinity of delta t by dt, which is just the definition of our impulse function, that area there, that is going to be a value of 1. So this leaves us e to the minus I omega t. Well, we know that this only exists at an infinitesimal region round about the origin, so it's really as t tends towards 0. So we could really just replace that t there with a 0. So that would be e to the minus I omega t, which would be equal e to the minus I omega times the t, which is 0. So it's just be e to the 0. Anything to the power of 0 is just a value of 1. So whenever we find the Fourier transform of a little impulse, we get a value of 1. So what does that really tell us? Well, it says that if we were to have an infinitely narrow, infinitely high spike, then in the frequency domain it's equivalent to adding up every single frequency from minus infinity to plus infinity. So let's look at this geometrically. Now, you'll see this throughout the rest of the course, and if you've done the previous course on the Fourier and Laplace transforms, you'll be used to seeing this type of description. So I've done it in a little kind of three-dimensional sense. So we have our function here of time, so this is the time axis, and the function is delta t. And we have over here the frequency equivalent of this, so this is this function Fourier transformed. So we've got an omega axis here, and we know that the Fourier transform of delta t is a value of 1, so that's just 1. It goes off to plus and minus infinity. Now, in order to go from here across to here, what we did was the Fourier transform, we integrated it and multiplied by e to the minus I omega t. Now we know that e to the I omega t is actually equal to cos omega minus I sine omega. But as we said before, this function here is a purely even function. So if we integrate an even function from minus infinity to infinity, we get a value. But if we integrate an odd function from minus infinity to infinity, we get a value of 0. So the sine omega t is going to be an odd function. The delta t is an even function, so even times odd becomes an odd. So it means that the sine omega t part of this here just disappears. It becomes 0. So in this instance here, what we have here is all that's left from the e to the minus I omega t is the cos omega t. So this here represents that cos omega t, and this is a cos omega t surface. So there's the omega axis, which is just this axis here. That's the t axis, which is this axis. This is a cos omega t surface, and it's modulated by this little spike. So the only thing that's going to be left of the cos omega t surface is this little central part here. Okay, and of course you're integrating it in that direction, so the only part of it is this here. So we're just basically looking in and taking the shadow of this here onto the frequency axis, so that gives us a value of 1. So I talked through that quite quickly, and if you have a look at a previous video when I talk about even and odd function, and I talked about the ethos of the type of derivations we're going to do in the three-dimensional graphical approach, then that will become more apparent to you. So now we know what the Fourier transform of a simple impulse looks like. We know we're going to create an impulse train, and that impulse train is made up of delayed impulses, so we delay it in time by a factor of the period t. So we're interested in finding the Fourier transform of a delayed impulse now. So we just write down in terms of an analytic derivation. Now also in a second we'll look at a graphical version as well. So we're going to integrate the function. Well, what is our function? Our function is our delayed impulse, which is delta t minus t. So this is our delayed impulse shown here. Well, it's delayed by a factor of t, and this is the height, delta t minus t. And when we take the Fourier transform, we integrate from minus infinity to infinity, e to minus I omega t by dt. Now, we know that the value here is only going to be a value of 1. That is the area here, integral from minus infinity to infinity of delta t minus large t by dt. Well, that's going to be a value of 1. Okay, so that's just the area under the impulse. But the e to the minus I omega t, well, in this instance here, this only exists at a point where t, that is the axis here, is equal to some value large t, which is just the delay. So that becomes e to the minus I omega large t. So that's just 1 times e to the minus I omega t. So that means that whenever we Fourier transform a delayed impulse, we get an exponential function in the frequency domain. Now we could do the same thing here with a function in the frequency domain. Whenever we delay a function in the frequency domain, it is equivalent to an exponential function in the time domain. Although we're not bothered with this for the moment, we could just look at the top one first of all. So let's have a wee look at that graphically, and it'll be more intuitively obvious whenever we see it in a graphical format. So what we have here is the time axis. So the bottom one is a function of time, which is just our delta function, which is delayed. In this sense here, we've delayed it by this factor of t1. And the drawing at the top, this is a Fourier transform of this delayed function. And the Fourier transform, we've done it graphically in 3D. So we've got the amplitude up here, and we've got the frequency along here, and we also have the imaginary part of the amplitude there. So this is the real part, and this is the imaginary part. Now, if we had just been looking at delta t, which was sitting at the origin, then this would be a straight line. So we just have a straight line going on from minus infinity to plus infinity. So we'd have every single frequency of the same amplitude. Now, whenever we delay that impulse, the effect of delaying it has the effect of adding linear phase onto the frequency domain equivalent. So what happens in effect is that if we were to think about this straight line here as being made up of an infinite number of little phasors, then whenever we shift a function in the time domain, these phasors start to rotate, and you can see the rotation of these phasors here. So at the positive axis, the phasors start rotating in this direction, and in the negative axis the phasors start rotating in this direction. So what happens is you get this curving, and eventually you get a corkscrewing effect, and that corkscrewing effect is just the exponential function, the complex exponential function I should say. So that's it delayed by a factor of t1. So let's have a look and we'll see it delayed by a factor of t2. So we've delayed it by an extra factor of t2. So now what's happened is this straight line here, all the phases have started rotating, and you have this corkscrewing effect. So this here in effect is our complex exponential. Now if you've looked at the Fourier and Laplace transforms course, you'll have seen there's a full video on this complex exponential which shows this effect here of the corkscrewing effect. So you can see where we're going with this. We know that the delayed impulse is going to give us a complex exponential in the frequency domain like this, and we know we're going to create the impulse train by adding up lots of these delayed impulses, and they're all delayed by a particular period. Now you might look at that and think, well, it means in the frequency domain we're going to be adding up lots of these complex exponentials, which we are, and it looks initially like we're going to end up with some very complicated function. But it turns out that whenever we work out the Fourier transform of an impulse train, we actually get another impulse train in the frequency domain. So it's maybe not intuitively obvious why it is that whenever we add up all of these complex exponentials that we end up with another impulse train, just like this impulse train at the bottom here. Well, we're going to have a wee look at that next. So why is it that when we add up all of the complex exponentials in the frequency domain, we end up with an impulse train? it's not intuitively obvious that that will be the case. So let's look at this example here. We've got an impulse train here. So this is the time axis, and there's a 0 point there, and we've got a few impulses in the positive axis and a few impulses in the negative axis. Now what we have here is a cos omega t surface. So whenever we were doing the Fourier transform of this impulse, we multiplied it by e to the minus I omega t, but as we mentioned before, the e to the minus I omega t has got a cos omega t and a minus I sine omega t. So the sine omega t, well, a sine is going to be an odd function when you and whenever you multiply that odd function by this function here, which is an even function, we get an even times an odd as an odd function, and we integrate that between minus infinity to infinity, so that whole thing becomes 0. So the sine component of the e to minus I omega t just disappears. So all we're left with is the cosine component of that e to the I omega t, and we can actually draw that cosine component out, and that's it drawn out there. Okay, so this is the frequency, so that's omega, and this is the time axis t, and we've just got all of the frequencies ranged from plus and minus infinity in the omega and plus and minus infinity in the t. But of course this is only going to be modulated at certain points, so it's only be multiplied, so it'll be 0 in between these points. So we'll have this point here, the first delta t would modulate, and we would get this here, and then the next one come along, we would modulate it, and we would get the next cos omega t, and that's the next cos omega t, and so on and so forth. And as we work up the way up this axis, the frequency just increases, and the same in the negative direction, and we can see that this is creating another cosine function. So part of the cosine function just goes down below the line there, so that's why you can't see it there, and we head off to infinity in this direction as well. So whenever we do the Fourier transform, we take this function here, which is the impulse train, we multiply it by e to the minus I omega t, which is only the cos omega t in this instance, and then we integrate it from minus infinity to infinity with respect to time, so we integrate it in this direction. So in effect we're adding up all of these little cosine functions, and as when we add up all of these little cosine functions in this direction, then my contention is that in the frequency domain this is equivalent to just a little another impulse train in the frequency domain. So let's go ahead and we'll see what happens whenever we actually go and add up all of these little cosines. So what we have here is our time domain function. So this is just our impulse train. There's no one at 0 for some reason, but there's one there at 0, and we have all of these other impulses here. Okay, and this here is the frequency domain, and this is all of the cosines. So if you like, if we go back up to the previous drawn here, that's equivalent to looking in from, say, this direction, and we can see this cosine here, and this one, and this one, and this one, and this. So you can see all of the cosines here, and you can see all of these ones at this side as well. So we're looking in this direction, and what do we see? We see all of the cosines. So what we want to do is we want to add up all of those cosines. So let's go back to the last drawing, and we can see we actually have an equation here which we can actually derive, but let's go and have to look at it intuitively. So we come back here, we want to add up all of these cosines. Okay, so there are only cos omega t's, so that's a lot of cos omega t's there, right? And then we're going to have a value here of 1, so it's going to be 1 plus all of these cos omega t's and all of these cos omega t's, but this is symmetrical, this, so we can flip this side onto that and it's just the same. So that's equivalent to adding up twice just one side. Okay, so what we can do is we can write that down here, and we've got that equation here. So we're going to have twice the value from n equals 1 to infinity over cos n omega t, and then we've got the 1 in the middle as well, so the 1 is just the central portion here. So this is really what we want to look at in the frequency domain, and we want to see what exactly that's going to look like whenever we've added up all of these terms. So let's just recap on things before we get lost. We looked at the delta t, we found the Fourier transform of the delta t as a value of 1. we looked at a delayed impulse. We found that the delayed impulse was equivalent to adding linear phase onto this, so it gave us a complex exponential, which just looked like a corkscrew. So the Fourier transform of this is a complex exponential, e to the minus I omega nt. So what we can do then is we can say that we can create the impulse train by adding up lots of these little delayed functions. So that's all the delayed functions, and we're adding them up between n equals minus infinity to plus infinity. So the equivalent for this in the frequency domain is just the same as just adding up all of these complex exponentials. So we've added up the complex exponential, and we've said that we don't really know what that's going to look like. It's going to be, well, we've actually said that it will look like an impulse train, but we don't have any intuition as to why that's the case. So in order to build intuition, we looked at this equation here and we said, well, that's equivalent to adding up all of the cosines. And then we said that because of the fact that the surface is symmetric, that's equivalent to the equation 1 plus 2 times the sum of all of the cosines. And now we're going to go and have a look at this in a graphical calculator and see what this looks like. So if it all works out, then this here should be just an impulse train in the frequency domain. So let's see what happens when we start adding up cosines of integer multiples of frequency. So we've got one cosine here, so this is cos x. Let me go over a wee bit. Now if I was to change this and make it cos x plus cos 2x, we would get this here. And already straight away you can see that we're starting to focus the power at just one point. So if that went up to cos of 3x, so with cos x plus cos 2x plus cos 3x, you can see the signal's being concentrated in the one area. So if I went to the final one here, we'd have our cos x plus cos 2x plus cos 3x plus cos 4x, and you can see we're starting to get a single point here and a point over here as well. So let's go on and we'll have a wee look and see what happens when we take this up to 30 or 40 values. So this is our function here, 1 plus 2 times the sum from n equals 1 to m of cos nx. So we're going to adjust the value of m so it adds in more and more cosine terms. So that's 1 at the moment, and there's 2, 3, 4 and so on and so forth. So you can see that all of the energy has all been focused at single points. So we can see quite clearly here then that if we add up all of these cosine functions, then in the frequency domain it's just going to tend towards an impulse train. So you can see quite clearly from this then that the frequency domain equivalent of an impulse train of the time domain is another impulse train. So now we know intuitively that if we have an impulse train in the time domain, when we Fourier transform it, it gives us an impulse train in the frequency domain. So let's go ahead and we'll look at this analytically. So we know that the impulse train in the time domain is a periodic function. So if it's periodic, it must have a Fourier series. So what we're going to do is we'll work out the Fourier series of this periodic function. So this is the complex Fourier series written out here. So the f of t is the sum from n equals minus infinity to infinity of a cn e to the in omega t. And we can able to generate the frequency domain amplitudes by this equation here. So if you've done the course in the Fourier and Laplace transforms, then we've derived these two equations in that course. So you can always go back and have a little look at that. So we're taking the function here, which is our impulse, an impulse train in the time domain, and we're working out what the Fourier series amplitudes are going to be. So we take our f of t, we replace our f of t with our impulse train, which is the sum from n equals minus infinity to infinity over delta t minus nt. So this looks a bit scary, but it actually simplifies quite simply, because if you note that this value here, t upon 2 to minus t upon 2, well, that's only going to include one impulse, and it's only going to include the one at the origin. So if it only includes the one at the origin, it means that the minus nt section can just disappear, and we're not bothered about any of the rest of these impulses, only the one at the origin. So this is going to simplify to the integral from minus t upon 2 to t upon 2 of the delta t minus in omega t by dt. So another thing to note as well is that this delta t here is equal to 0 everywhere else other than the origin. So it means that rather than looking at this integral from minus t upon 2 to t upon 2, we can extend the limits of this integration from to minus infinity to plus infinity. So now we're simply left with this equation here. Now we already know that this delta function is defined such that the integral from minus infinity to infinity of delta t by dt is equal to a value of 1. And we know that it's only defined at t equals 0, so if we put the t equals 0 in here for the e to the minus in omega t, then we're going to simply be left with the 1 upon t times e to the 0, which is equal to 1 upon t. So that means that if we put this back into our function for f of t, we'll simply be left with our 1 upon t times the sum of e to the in omega t. But we've already shown that if we sum up all of these exponentials here, we're simply going to be left with an impulse train in the frequency domain. So we started off with our delta t minus nt, the sum from n equals minus infinity to infinity, so that's our impulse train in the time domain. So we'll simply be left with this sum of exponentials, which we've shown as just an impulse train. So this will be the impulse train in the frequency domain, which will be delta omega minus n omega s. So an impulse train in the time domain will give us an impulse train in the frequency domain. And the thing to note here is that the distance between each of the impulses in the time domain is given by this nt, and the distance between the impulses is going to be given by this n omega s. Omega s is 2 pi upon t. So we can see here there's an inverse relationship between the distance between the impulses in the frequency domain and the time domain. So it means that if the impulses in the time domain are very close together, then the impulses in the frequency domain are going to be very wide apart, because omega is 2 pi upon t. So there's an inverse relationship between the omega and the t. So it means then also if the impulses are wide apart in the time domain, they're going to be very narrowly spaced in the frequency domain. So an impulse train in the time domain will give you an impulse train in the frequency domain. And in the time domain, if the pulses are very close together, then in the frequency domain they'll be very wide apart. If in the time domain the impulses are very wide apart, in the frequency domain they'll be very close together, because there's an inverse relationship between the time and the frequency. So thank you for listening to this video. I'll get you on the next video.